Imagine this. Outside, a raging blizzard howls through rural Finland. Temperatures plunging to -30°C. Snow piling up in drifts that bury roads and fences. But inside a modest farmhouse, a farmer sleeps peacefully under a warm blanket. His family cozy and comfortable. No roaring furnace, no skyrocketing gas bills, no expensive heat pumps or $40,000 solar arrays. His secret: 3 years ago, he did something his neighbors called crazy. He filled a steel silo with ordinary sand, ran pipes through it, and connected it to his home. Last February, his heating bill was exactly zero. This isn't science fiction. It's a simple, powerful sand battery thermal storage system that's quietly transforming how off-grid and homestead families stay warm. And today, you'll discover exactly how to build one yourself. They told you that surviving winter means expensive gas lines, high-maintenance heat pumps, or installing a massive $40,000 solar array just to keep your home warm. But right now, in a remote corner of rural Finland, a farmer is sleeping soundly through heavy blizzards with absolutely no heating costs. 3 years ago, he took a steel silo, filled it with sand, threaded pipes through the mass, and linked it to his house. His neighbors laughed and thought he had lost his mind. His energy company dismissed it as a joke. Yet when the coldest month arrived, his bill read $0. This story should worry the companies selling you gas and electricity. The system costs around $300 to build, using materials available at any local hardware store. Once charged, it holds usable heat for weeks with zero electricity needed to maintain it. Stay with me through this complete guide. By the end, you will have a full step-by-step understanding of how to construct your own sand battery, plus clear insight into why the survival and homesteading community has been quietly installing these systems for over a decade, while others continue paying high monthly bills. Before diving into the construction details, let's clarify exactly what a sand battery is, because there is considerable confusion online. A sand battery is not an electrical battery that stores electricity. Instead, it stores thermal energy, pure heat, using sand as the storage medium. The concept builds on basic physics, known as specific heat capacity. Every material has a different ability to absorb and retain heat. Water stores heat effectively. Concrete does too, but dry, fine-grained sand excels at holding heat and can be heated to extremely high temperatures without problems. Unlike water, sand never boils, evaporates, or causes corrosion inside your pipes. Dry silica sand has a specific heat capacity of approximately 830 joules per kilogram per degree Celsius. This means that raising 1 kilogram of sand by 100 degrees Celsius stores about 83,000 joules of thermal energy. Scale this up practically. A silo containing 1 metric ton, 1,000 kilograms of sand heated to 500 degrees Celsius holds roughly 415 megajoules of thermal energy. For context, the average American home consumes around 50 megajoules of heating energy per day during winter. 1 ton of properly heated sand could therefore theoretically provide warmth for more than 8 days without any additional energy input. A Finnish company called Polar Night Energy has developed commercial-scale versions of this technology. Their system uses a large 4-meter wide by 7-meter tall steel silo holding 100 tons of sand, charged to 500 to 600 degrees Celsius with excess wind and solar power. It provides district heating for multiple buildings. We are not building that industrial version here. Instead, we focus on a practical homestead scale system that is smaller, far cheaper, and can be completed in a single weekend. The underlying physics remains exactly the same. Before going deeper, it is important to address some common viewer comments and concerns. One viewer who identified as Amish wrote that the idea seemed completely untrue. This feedback deserves respect. Amish communities possess deep hands-on knowledge of building, heat management, insulation, masonry, and passive heating systems that surpasses many modern engineers. When experienced builders push back, it is wise to examine the claim carefully rather than dismiss it. The Amish rely on proven traditional technologies like wood stoves, masonry heaters, and radiant floor systems. These methods work exceptionally well, and no one disputes their effectiveness. The sand battery is not positioned as as a complete replacement for these established approaches. Rather, it serves as a powerful complementary system. Interestingly, a traditional masonry heater operates on a very similar principle to the sand battery. You burn wood intensely for a short time. The dense mass absorbs massive amounts of heat and then radiates gentle warmth for 12 to 24 hours after the fire dies. The sand battery follows the same core idea, using a thermal mass to store and slowly release heat, but at a larger scale and with flexible charging options. To the Amish viewer and others with traditional building wisdom, the sand battery concept actually aligns closely with the principles you already practice daily. Another comment joked about typing with wooden sticks like an Amish forklift, highlighting a fair underlying question. Who is this system really practical for? The honest answer is people who have access to some land, a basic workshop, and the willingness to perform physical work. If you live in a city apartment without outdoor space, this project is not suitable. But for homesteaders, cabin owners, rural property holders, or anyone building off-grid, this ranks among the highest leverage projects available. A third comment correctly noted that fertilizer is petroleum-based, referencing the Haber-Bosch process that uses natural gas. This is accurate and undisputed. However, it is irrelevant to this discussion because we are focusing solely on thermal energy storage using sand. No petroleum or complex chemical processes are involved. The inputs are simple heat sources you likely already have. This reminder to question everything remains valuable. When claims of free energy appear, always examine the actual required inputs. For the sand battery, once built, charging comes from solar, wood, or other existing heat sources you control. Now let's prove the concept by walking through the complete build process. Here is the full materials list first, followed by detailed step-by-step instructions. You will need a steel drum or silo. Start with a minimum 55-gallon steel drum for basic testing. For meaningful home heating, choose a 250 to 500-gallon vertical steel tank. Properly cleaned used propane tanks work well. New 250-gallon vertical tanks typically cost $150 to $250. Dry, fine-grained silica sand. Avoid construction sand with moisture or beach sand with salt. Use kiln-dried silica sand. For a 250-gallon tank, plan for 800 to 900 kilograms, roughly 25 to 30 bags of 30 kilograms each. Cost $40 to $70. Steel pipe for the heat exchanger coil. Use a schedule 40 black steel pipe, 1/2 inch or 3/4 inch diameter. You will need 20 to 30 feet for a basic coil, preferably up to 40 feet. Cost $30 to $50. High temperature pipe fittings and couplings rated above 300 degrees Celsius. Use only steel threaded fittings. Cost $20 to $30. Ceramic fiber insulation blanket, minimum 4 inches thick. Cost $40 to $60. 26 gauge galvanized sheet metal for outer cladding. Cost $20 to $30. Connection hardware for your chosen heat source. Outlet piping to connect with your home's heating distribution system. Total estimated material cost $250 to $310. Tools required include an angle grinder, MIG or stick welder, pipe wrench set, drill with metal bits, pipe bender, and full safety equipment, gloves, eye protection, and N95 respirator. Site selection is crucial because the system produces significant heat and must never be placed inside living spaces without proper fire-rated separation. 3 main options exist. Option 1. Install inside and out buildings such as a small shed or workshop next to your house. Run insulated pipes underground to your home. This setup offers easy access and protection from weather. Most people choose this approach. Option 2. Bury the tank underground. Earth provides excellent natural insulation and weather protection, though maintenance requires digging. This works best in very cold climates where maximum heat retention matters most. Option 3. Place it in an attached utility room with concrete or masonry walls and proper fire separation. Maintain at least 24 inches clearance from all combustible materials. For most builders, the outbuilding option is fastest. Construct a simple 8 by 10 foot shed on a reinforced concrete slab at least 4 inches thick. Allow the slab to cure for 7 days before setting the heavy tank. A filled 250-gallon unit weighs over 1 ton. For underground pipe runs, dig trenches at least 18 inches deep below frost line and use pre-insulated pipe sleeves. The heat exchanger coil is the most technical component. This pipe system inside the sand handles both charging, adding heat, and discharging, extracting heat for your home. You can use a single coil for both functions or separate coils. A single coil is simpler for most homestead systems. Step 1. Calculate coil length. For a 250-gallon tank, use at least 25 to 30 feet of 1/2 inch pipe. 40 feet provides better performance through increased surface area. Step 2. Bend the pipe into a helical coil with a 6 to 8 inch centerline radius. Ensure 2 to 3 inches clearance from tank walls on all sides. The coil should run vertically with inlet at the bottom and outlet at the top. If you lack a pipe ender, use straight sections with elbow fittings. Step 3. Prepare pipe penetrations. Weld entry and exit points through the tank wall using pipe nipples and threaded couplers. These welds must be strong, airtight and high temperature rated. Have a qualified welder inspect them. Step 4. Perform a leak test. Cap one end, pressurize to 50 pounds per square inch with compressed air and check all joints with soapy water. No bubbles means success. This step is critical because fixing leaks after filling with sand is extremely difficult. Step 5. Carefully lower the centered coil into the tank. Use wire ties if needed to suspend and secure it. Maximize sand contact and minimize air gaps. Filling the tank follows 2 unbreakable rules. First, the sand must be completely dry. Any moisture turns to steam at operating temperatures, creating dangerous pressure and accelerating corrosion. Use only kiln-dried silica sand. If unsure, dry it on a tarp in direct sunlight for a full day. Second, fill slowly in 6-inch layers, compacting each layer thoroughly with a steel rod or plate compactor. This eliminates air pockets that would reduce efficiency. Fill to within 6 inches of the top to allow for expansion. Seal the top with a bolt-on steel plate and high-temperature silicone rated for 500 degrees Celsius or higher. Insulation is essential. Without quality insulation, heat dissipates in hours instead of weeks. Apply a base layer of 4-inch ceramic fiber blanket rated for up to 1260 degrees Celsius around the entire tank, including bottom and top. Place a 2-inch ceramic fiber board under the tank. Secure side layers with high-temperature adhesive or stainless wire. Wear protective gear as ceramic fiber can irritate skin and lungs. Add a second layer of 26-gauge galvanized sheet metal cladding fastened with screws and sealed with high-temperature silicone. Finally, insulate all connecting pipes thoroughly. Poor pipe insulation is the most common reason systems underperform. Connecting to your home depends on your existing system. For radiant floor heating, use a stainless steel plate heat exchanger with 2 12-volt DC circulation pumps, one for the battery loop and one for the floor loop. These pumps can run on a small solar panel, keeping everything off-grid. For hot water baseboard heaters, use the same heat exchanger setup. For forced air systems, install a water-to-air heat exchanger in your air handler. Install an Aquastat temperature sensor with relay on the output pipe. Set it to activate pumps only when output exceeds 60 degrees Celsius for radiant floors or 70 degrees Celsius for baseboards. This prevents circulation of insufficiently warm fluid. Charging methods offer great flexibility. Solar thermal uses evacuated tube collectors to heat glycol, which circulates through the coil. A 20-tube panel can produce 150 to 200 degrees Celsius fluid on sunny days. Rocket mass heaters provide another excellent option. Route hot exhaust gases through the coil before the flue, capturing wood heat efficiently. Excess solar PV electricity can power an immersion heater element inside the sand or an oil-filled pipe, converting power to heat at nearly 100% efficiency. Most homesteaders charge the battery 2 to 3 times per week in winter using available sources. Maintaining sand temperature above 100 degrees Celsius keeps extraction efficiency high. Performance numbers are important for realistic expectations. A 250-gallon sand battery with 900 kilograms of sand charged to 200 degrees Celsius stores about 134 megajoules. A well-insulated small home in a cold climate might use 30 to 50 megajoules per day. This means one full charge provides 2.7 to 4.5 days of heating. Charging every 3 days maintains steady coverage. Larger or poorly insulated homes will see shorter duration, so results vary. The sand battery rewards tight building envelopes. Every improvement in insulation and air sealing cooling multiplies the system's effectiveness. Maintenance is minimal and represents a major advantage. There are no burners, no combustion part, and no ongoing fuel requirements. Annually, isolate the loop, pressurize the coil to 30 pounds per square inch, and check for pressure drops over 30 minutes. Stable pressure confirms no leaks. This system represents practical energy independence. It uses abundant, cheap materials and proven physics. While not a universal solution for every living situation, for those with land and the willingness to build, it offers genuine freedom from high heating bills. The farmer in Finland proved it works. Now you have the complete knowledge to make it work for your homestead too.